precise, engaging binary, we are directly observing an adversary's attempt to hide. Our goal is to peel back these layers of obfuscation and to systematically deconstruct the hidden payload underneath. To achieve this, we rely on a strict three-stage pipeline: static property examination, behavioral observation, and memory forensics. But before we examine a single byte, we have to enforce the cardinal rule of this discipline. A malware sample must never be executed on a host machine, and it must never touch a production network. We contain the threat by building a dedicated virtual machine, configured exclusively with a host-only network adapter. This network diagram illustrates how a host-only adapter physically severs the external connection to the underlying host hardware. It locks the virtual machine inside a closed network loop, permitting internal routing for our lab tools while guaranteeing zero external internet access. This creates an operational paradox. Modern malware often requires an active connection to its command and control infrastructure. Without it, the payload may refuse to detonate, keeping its true behavior hidden from the analyst. We solve this by introducing network simulators like INetSim into the loop to safely intercept the outbound telemetry. INetSim deceives the malware by serving dummy DNS and HTTP responses. The malicious process receives a response, assumes it has successfully reached its control server, and continues execution, while every packet remains trapped within the sandbox. Establishing this architectural isolation is the absolute prerequisite for the entire pipeline. It allows us to watch a catastrophic infection unfold in real time, capturing every behavioral indicator without risking an actual system compromise. With the environment secured, we begin with static analysis, inspecting the binary's internal structure and metadata without allowing its code to execute. The primary focus of this static triage is the Portable Executable, or PE file format, which acts as the core data structure for all Windows binaries. This structural diagram of the PE format illustrates where malware authors attempt to conceal their payloads. By packing or encrypting the original code, they introduce distinct mathematical anomalies into the file's image section header array. The most reliable indicator of a packed binary is a mathematical discrepancy in its size parameters. If we observe a section where the size of raw data on disk is 0 bytes, but the virtual size required in memory is massive, we have found an anomaly. A section that takes up no space on disk but requests huge amounts of RAM is effectively an empty container. This size discrepancy mathematically proves the section is engineered to be populated dynamically with unpacked code at runtime. We then shift our focus to the Import Address Table, or IAT. This table lists the specific external Windows API functions a program requires from the operating system to operate. Encountering a zero-length import table in a Windows executable is a severe structural red flag. It indicates the binary is deliberately hiding its capabilities by resolving its required API calls dynamically while running. This visual maps how we leverage the IAT to generate an imp hash. This is a unique cryptographic hash computed directly from the specific ordered list of imported DLL functions requested by the executable. Because the imp hash relies entirely on the import order, two completely distinct malicious payloads will output the exact same imp hash if their authors utilized the same underlying packing tools or development frameworks. This highlights the principle of asymmetric visibility. A threat actor can encrypt their code to obscure its execution, but they cannot hide the structural math required by the operating system to load their file. Once we exhaust the static properties, we move to behavioral analysis, intentionally detonating the malware within our isolated environment. The objective here is to document the precise footprint the executing binary leaves across the file system, the Windows registry, and the active process tree. To capture this telemetry, analysts rely on sysinternal's process monitor, or ProcMon, to record thousands of system events per second in real time. Our immediate priority during detonation is identifying persistence mechanisms. We are searching for the specific registry modifications or file system drops the malware executes to guarantee it survives a system reboot. This interface shows the most common persistence indicator, a direct write to the registry. Analysts look specifically for a malicious modification to the current version run key within the HKCU software hive. Capturing this specific registry operation is highly valuable because the string written to the run key provides the analyst with the exact local file path of the persistent payload. Alongside registry changes, we monitor the process startup behavior for the creation of a named mutex. A mutex is a locking mechanism. Malware utilizes a named mutex to check if the system is already infected, ensuring only one instance of its operational code runs on the compromised host at any given time. Behavioral analysis acts as the critical bridge in our workflow. It translates the dormant potential we observed during static analysis into an actionable, time-stamped timeline of a system compromise. Physical disk analysis has distinct limitations. Highly evasive malware can unpack itself dynamically or inject its malicious code directly into legitimate Windows processes, leaving no physical footprint for antivirus tools to scan. To counter this, we turn to memory forensics. By capturing the volatile RAM and analyzing it with the volatility framework, we gain an unfiltered view of the system's actual running state. When hunting for injected code, the primary tool in volatility is the Windows.malfind plugin, which we execute against the captured memory dump. The malfind plugin locates anomalous memory inside svchost.exe. We search for page execute read-write permissions, indicating actively allocated space. Finally, we verify the MZ header, 4D5A. Legitimate DLLs are mapped from the disk, not injected dynamically. Finding this exact combination of read, write, execute permissions alongside an embedded MZ header conclusively proves that a malicious executable has been completely hollowed out or injected directly into the system process. This completes the analytical pipeline. We leverage static structures to locate mathematical anomalies, utilize behavioral monitoring to map persistence mechanisms, and deploy memory forensics to extract the hidden code. By rigorously combining these three independent methodologies, we systematically strip away the adversary's ability to conceal their actions. We dismantle the obfuscation, expose the payload, and defeat even the most evasive threats.